In this video, we're going to go through an introduction to hypothesis tests, as well as an example showing you the different parts of a full hypothesis test for a proportion. So some pieces that we start with these hypothesis tests is we start with the hypothesis, meaning we start with some assumed value for our population proportion. So we're going to assume something is true, or we have this kind of base value that we assume would come out from a sample if we took a sample collecting this proportion. What we want to do is see, how does our sample statistic compare? Because how our sample statistic compares can tell us two different things. So these two scenarios that are going to come out from these hypothesis tests, what we're going to do is, if we assume this value for our population proportion, what we can do is see what would happen if we use the same sample size that we used for our sample statistic and assumed this value of p would come out. So we're essentially making a sampling distribution where we would expect p to come out, and then there would be some distribution of how things would behave. And we would look at the same exact thing for the second scenario as well. So how would these samples behave given that we assume this population proportion is true? What we want to do is see, how does our sample statistic compare? Because they could provide evidence that this distribution's actually false. So one scenario would be, what if we took our sample statistic and it landed somewhere close by our population proportion? What this would basically show is that we took a sample, and out of random variation, this proportion's pretty likely. In fact, to prove that, what we would do is find this probability. What's this probability of seeing that sample statistic, or even larger? And what we could see is that that is a large probability, which means this is showing not extreme results. That sample we took was absolutely possible if that population proportion is true. So with this scenario, we wouldn't have any evidence that the distribution is false. We don't necessarily have evidence that this distribution is true, and that's something that we'll talk about a lot, but no evidence that p is false. Because basically, even though our sample statistic didn't come out to be exactly equal to p, with this sampling distribution we could see that it was close, so it was a likely outcome given p is accurate. The other case that we can see with these hypothesis tests is, what if we found this distribution for how our population proportion would be behaving with these sample sizes, and we have this sample statistic, and it is way out here somewhere. Meaning we took a sample that would not be likely at all under this distribution. However, we saw those sample results had a very low probability of occurring, but we took a random sample and we saw that value for p hat come out. So we know we have the sample value. So what this is showing is extreme results. We took a sample and got something extreme out, which means we start not trusting this distribution that we have. We start not trusting that assumed value. So the idea is, our sample statistic value is so unlikely if that proportion is true. So if that is truly our population proportion, this sample we took is so unlikely, this gives evidence to reject that value that we have for p. We would reject that that's the actual value and that we should actually have some other distribution occurring. So these are two scenarios. What we want to do is work with this assumed value and how samples should behave and see, do we have this first case where we have a sample statistic that's actually close by and doesn't really give extreme results. So with that, we don't really have evidence to reject that value of p. Or do we have the second scenario where our sample statistic was so unlikely that this value of p just can't be true, and something else is happening? in the case that I drew there, we'd have evidence that our population proportion is actually a larger value by getting that larger sample statistic out. So we're going to end up with two types of conclusions. This first conclusion is one where we'd say fail to reject the null hypothesis, and this second case is where we would say reject the null hypothesis. We'll come back to that once we get our notation. So let's talk through an example of how you could see these scenarios come up. So we have the 2013 NFL season. The home team won 153 of 245 regular season games. So right there we have this sample statistic coming through. So in this chapter, we'll determine if this is evidence of a home field advantage. So as you can probably guess, evidence is a bit ambiguous, and we'll get that a little more detailed later on of how we know whether or not we have evidence or not. But for now, we'll go through kind of an obvious case of that we definitely have evidence or we definitely don't have evidence. So what we want to do is determine the probability of seeing this sample, assuming that there's no home field advantage. So let's talk about this proportion that we're analyzing first. So this proportion that we're looking for is just this proportion of games won by the home team. And then what we have is this sample statistic for the 2013 NFL season, where we saw 153 out of 245, which as a decimal will be a 0.6245. So what we would assume is true is that it would be a 50-50 chance. Doesn't matter if you're the home team or the away team, you have a 50-50 chance of winning the game. And we're going to kind of rule out any skill here. It's in terms of just location of play, it should be 50-50. So that's what this is describing here, is what if we assume there's no home field advantage? In terms of our population proportion, what we're assuming is that our proportion is 50%, to show that there's no advantage one way or the other. So what we want to do is, we see from our sample statistic that we got this 0.6245, which is definitely larger than 50%. But what we want to find out is that number significantly larger? Is it this case up above, that first case, where it's actually close by and we could totally get that 62.45% just from a random sample? Or is it the second case where 62.45% is significantly larger than 50%? So with that, we'd start having evidence that there is a home field advantage. So we need to see how extreme is this sample that we have. Some notation. The first step that we do with our hypothesis test is we state a null hypothesis, which we state the null hypothesis with a H with a subscript of 0. And then there's an alternative hypothesis, which the notation for that is H with a subscript of A. So in general, the null hypothesis is what we assume is true. And then for the alternative hypothesis, that is what we want to prove. So it's what we're trying to gain evidence for. So in our notation, you're going to have null hypothesis and alternative hypothesis. You might sometimes see these described in words with a sentence. What we're going to use is notation. What we're going to do is describe what we assume is true for P. And as we talked about up above, we assume that that is equal to 0.5. Then for our alternative hypothesis, if we're trying to prove that there's an advantage in terms of this proportion of games won by the home team, we want to show that this proportion is larger than 50%, since that would be the idea of a home field advantage. So our notation for that null hypothesis is the idea of no home field advantage. And our alternative hypothesis is a statement that says that there is a home field advantage. So notation for null and alternative hypotheses, and in the next video we'll practice just making null and alternative hypotheses, but the general structure that you're going to see for the null hypothesis, you're always going to have your population proportion is equal then to some number. We're going to have some assumed value for our population. In the alternative hypothesis, we want to compare that proportion to the same number. What's going to change is the symbol in between. And there's going to be three options for the symbol in between. Either we'll try to prove that it's larger, less than, or not equal to that number. In terms of which symbol to use, check the wording of the problem. So for us, it had to be more than to show the idea of winning more than 50% of the games. If we were looking into a case of home field disadvantage, like trying to show that they win less than half the games, then we would use the less than symbol. And then the does not equal symbol comes through when we're just trying to show change. If we just wanted to show that it's not 50%, so not necessarily trying to prove that it's larger or smaller, we'd use the does not equal sign. So this is our first step to all hypothesis tests, stating the null and alternative hypotheses. So null is what we assume is true, and it's this alternative hypothesis that we're trying to prove correct. And that's where, in terms of our two pictures above, this first case shows that our proportion's larger, but it's just not significantly larger. And this second case is where our value's larger and it's significantly larger. So there's also this difference in significance. This case would be significant where we have unlikely results, but this case over here is not significant. So while our sample proportion is in fact larger, it's not significantly larger. We're trying to gain evidence for this alternative hypothesis, and it's that this first case would have no evidence. The second case would have evidence because of that significance. So, to decide if there's a home field advantage, what probability do we need to determine? Well, that matches up with the picture that we drew up above. Basically, what we want to do is look at a distribution for how samples would behave, and specifically samples where we are taking samples of size 245 and with this assumed proportion of 0.5. We want to see that if we had them play 245 games and we expected a 50-50 chance, what would our number line look like? Which we'd have 0.5 in the middle, but in terms of a number line, we would need to know more about this sampling distribution. But it's once we get that distribution, we want to look for how does our sample compare. Wherever 0.6245 is landing, we want to see what's the probability of seeing that much larger than 50% or even larger. Because again, we can't find just the probability of 0.6245 because that would just be a line, and a line doesn't have any area. So instead what we do is go beyond the values. We say, what's the probability of being as extreme or more extreme than our sample? So to put this in words, this probability that we're looking for, which is going to be that shaded area, it's the idea of assuming that there's no home field advantage. Which, that's the idea of assuming that our proportion is 0.5. So assuming that's true, assuming our null hypothesis is true, what is the probability of seeing p hat, or of seeing specifically our sample statistic, so that 0.6245, what's the probability of seeing that value or more extreme? So what's the probability of our p hat or more extreme? So as large or even larger than that sample statistic that we're getting at. Now, something that we're going to do in this case is change over to our standard normal curve, just to make things a little bit simpler. So what we're going to do is adjust our number line here. So really in the middle, will be at 0, and then we'll have our usual standard deviations. But then what we're going to do is find a z-score for this 0.6245, so that we can always find these values on our standard normal curve. So that's going to be this one little extra step that we do in there, but it perfectly equates to this idea of having our sampling distribution as well. So with that, we're going to find a z-score, then we're going to find this area to the right of that z-score. And so we are going to need GeoGebra in this process in order to find this probability. So as a refresher of how to find z-scores, we take our data value minus the mean over standard deviation. Now this is going to change a little bit here in terms of how we calculate our z-score for using proportions and at the same time using a sampling distribution. So what our z-score is going to look like is, if you think about what our data value would be, that's our sample proportion. Then what we want to do is subtract the value that would be at the center of the distribution, our mean, which would be our population proportion, then divided by the spread of the distribution, which, if you remember from our topics on sampling distributions of proportions, our standard deviation, how we would calculate that would be the square root of p times q over our sample size. So that's exactly what we're going to put into our denominator here. I'm going to change one little bit of notation here. Where we're using p, we actually want to throw a little subscript of 0 there, so that when we work with p with a subscript of 0, you're looking at p from the null hypothesis. This just helps for when we look at our standard deviation in the denominator there, because you want to use the values from the hypothesis. So we'd want to take our p from the null hypothesis and q from the null hypothesis over our sample size. So what this will look like is a calculation where we're taking 0.6245 minus the proportion from our null hypothesis, which is 0.5, all divided by, and then this square root of 0.5 times 0.5 divided by our sample size, which was 245. Now, this can get a little complicated because you have a fraction within a fraction. I highly recommend using Desmos to organize this calculation. So with Desmos, what we could do is separate our fraction. And so in the numerator, we'll have that 0.6245, and then we're subtracting 0.5. Then in the denominator, we're going to have a square root, and that square root will have a fraction. It'll be a 0.5 times 0.5, and then in the denominator, 245. So I really like Desmos for this because it can show you exactly how it's laid out. So we're getting a z-score of 3.8975. And go ahead and take these to 4 decimal places for accuracy. So this z-score, 3.8975. So now what we have in terms of our information is, if we have our standard normal curve centered at 0, what we want to do is find this z-score of, which is going to be way out there at 3.8975, and we want to find the area to the right of that z-score. So what we're going to do is go to GeoGebra and find the probability of x being larger than or equal to that 3.8975 using our standard normal curve 0, 1. So let's go to GeoGebra. And we're looking for an area to the right, and we want to type in our value 3.8975 and enter, and that's given us a big old 0 out. So our probability is very close to 0. That is 0. Which, interpreting that, is telling us that there was pretty much a 0% chance of seeing our sample statistic. We go back up above here and talk about this probability we were trying to find. What we looked at is if that proportion is actually 0.5, if that's true for our population proportion, the sample statistic, the value of p hat equals 0.6245 has close to 0% chance of occurring. However, what we did though is we took that sample. We saw this sample statistic of 62.45%. So if there's nearly a 0% chance of that occurring, what that tells us about our assumption that this proportion is 0.5 is that that must not be true. If we took this random sample and saw this value that was pretty much impossible, our assumption is most likely wrong. So with that, we're starting to get evidence for our alternative hypothesis. We would say we start to have evidence for the alternative hypothesis, the fact that this proportion is probably larger than 0.5. We're starting to get this evidence that there is a home field advantage. And what we do in this process is reject that null hypothesis and say, there obviously isn't no home field advantage. We're finding evidence that there is a home field advantage. So the important piece to this process that we just went through is the probability. That's what it comes down to in our evaluation of whether or not we have evidence. It's this probability of 0 that's showing us very strong evidence for that alternative hypothesis. That value for the probability has a name, and that is p-value. The p-value is this probability of our observed sample, so seeing our value for p hat, given that our null hypothesis is true, which is exactly what we did in this last example. We said, if our null hypothesis is true with that p equals 0.5, how extreme is our sample statistic? And that value of how extreme comes down to that 0% chance of occurring. So it's going to be that probability that tells us whether or not we have evidence. So going back to our initial discussion of kind of these two cases, it's going to be this first case that will have a large p-value, which is connecting completely to the fact that we have this large area shaded here. Large area means a large p-value, which means a large probability of that sample statistic occurring. That all connects. Whereas in this second example, this would have a small p-value. Having the small area there links to a small probability of seeing our sample statistic, which links to small p-value. So this is where we go through this process of finding our value for the p-value, and then we have to interpret, is it large or small? So we'd have two options. When the p-value is small, that's when we go through this process of reject that null hypothesis, which we did up here, reject the null, and we have evidence for the alternative. So that falls through too. Evidence for alternative. If our p-value is not small, and in the video we'll talk about what is sufficiently small for p-value, but when the p-value is not small, we would say we failed to reject the null hypothesis, which means we do not have evidence for the alternative. So in our conclusions, when we make our sentences, we'll either say we have evidence for what's being laid out in the alternative hypothesis, or we don't have enough evidence. The key is that when we start these hypothesis tests, we want a small p-value. This small p-value leads us to strong evidence. And the smaller the p-value, the stronger the evidence. So the smaller the p-value, the stronger the evidence for the alternative hypothesis. So what we did up above with the NFL, this is the strongest evidence we could get out for a hypothesis test. To take a sample and basically say that that sample's impossible, it has close to 0% chance of occurring, that's the strongest evidence we could possibly get for our alternative hypothesis. Because we saw the impossible, if that null hypothesis is true, so that null hypothesis can't possibly be true. But then as p-value grows, that evidence becomes weaker and weaker. So, writing a conclusion for what we found. The key piece of information is that we got a p-value of 0 out, which p-value of 0 is very small. It's the smallest p-value. So with that, all of these pieces fall through. We reject the null hypothesis, which something I even like to do if you have your null and alternative hypothesis. So there's our null, here's our alternative. If we're rejecting that null hypothesis, we are literally just going, nope, that's not true. This is true. So this is where we have evidence for the alternative. So what we could write in our conclusion is we want to describe how we have evidence for this proportion being larger than 50%, or the idea of a home field advantage is what this translates to. When we say that we have evidence, we need to state the level of evidence. And with that, in our conclusions, we always need to state the p-value. So we would say with a p-value of 0, or really we should say with a p-value close to 0, anything's possible. I keep kind of saying it has close to 0% chance of occurring. So it's close to 0, even though it's showing up as completely 0 on GeoGebra. And then what we would say is there is evidence for the alternative. There is evidence of a home field advantage. And that would be our conclusion. So, to take you through the steps that we're going to do for our hypothesis tests, we'll be given wording that describes some assumption and some sample results. Then what we'll do is make our null and alternative hypotheses. Then we'll need to create a z-score for our value. With that z-score, you'll find a p-value. And once you find that p-value, you need to figure out, are we rejecting the null or failing to reject the null? And once you figure that out, you can make your sentence conclusion. Those are going to be the pieces we'll go through. In these videos, I'll show you many examples, and then the worksheets, even more examples with these.